Right now, atmospheric CO2 levels are rising rapidly and are projected to reach around 429 parts per million by 2026. These rising CO2 levels trap heat in the atmosphere, causing global warming and long-term climate changes. This growing concentration of carbon is already changing our planet. Oceans absorb about 25 to 30% of human-made CO2, which alters seawater chemistry and leads to acidification. As a result, marine organisms are being affected and many organisms struggle to survive. At the same time, rising CO2 levels damages infrastructure and agriculture, creating long-term economic problems. Most importantly, these challenges directly affect people. Rising CO2 levels and temperatures causes dizziness, headaches, and fatigue. It reduces alertness and overall productivity. So, climate change is not only an environmental issue, it is an environmental, economic, and a human challenge. The key question is not only how we reduce emissions, but also how we deal with the carbon already present in the atmosphere.
As we heard, removing CO2 already present in air is a critical challenge. To address this, we designed a fully functional direct air capture system that fits inside a compact 1 cubic foot cube. Before diving into details, let me quickly show you how our system works. Now let's break this down step by step. We begin with ambient air containing around 650 to 800 ppm of CO2. The airflow is created by a vacuum pump placed at the outlet, which pulls air through the system. The maximum airflow is about 9.4 standard liters per minute and passes through 3 main stages. Particulate filter, which removes dust and impurities. Silica gel dryer removes moisture, which could otherwise interfere in adsorption efficiency. Packed bed column, where CO2 is captured using a solid adsorbent. This packed bed is the core of our capture system. Now we'll tell you about the unique selling point of our system.
Our main innovation is modular cartridge system. Instead of removing adsorbent continuously, we designed the packed bed as a removable cartridge connected using lure lock mechanism. This allowed quick replacement in under 10 seconds and no direct contact with chemicals. Additionally, it is a completely sealed leak-proof connection, so maintenance becomes fast, safe, and plug-and-play, which is a major improvement over traditional system. To improve performance inside a small cube, we made 2 key engineering choices. The system operates under slight negative pressure, which helps prevent any CO2 leakage and ensure uniform airflow through the bed due to induced draft by the vacuum pump. We used PWM control on the vacuum pump, allowing us to adjust flow as needed and significantly reduce power consumptions. Now, once the cartridge gets saturated, it needed to be regenerated. We proposed a thermal vacuum swing adsorption system or TVSA. After regeneration, the cartridges are cooled and reused in the cube. So overall, our system is compact and highly user-friendly with a strong focus on modularity and safety. Now, we will walk you through how we selected the system parameters using simulations.
Simulations are essential because they allow us to predict system performance without conducting expensive and time-consuming experiments. We have developed an axial packed bed adsorption simulator which simulates the separation of carbon dioxide from an air mixture of carbon dioxide, nitrogen and oxygen gas. The model incorporates key physical phenomena like multi-component Toth isotherm for equilibrium, Ergun equation for pressure drop, and linear driving force kinetic for adsorption. So, how do we ensure the validity of the model that we built? The model was validated using adsorption parameters of zeolite 13x obtained from Aspen adsorption. The simulation results showed good agreement with Aspen adsorption, achieving less than 5% error in maximum saturation and an R-square value of 0.88. Using this model, we can optimize key design parameters such as the length to diameter ratio while considering constraints like pressure drop limits and flow rate limits. Now, let us see the outputs of our simulation. To simulate, we have considered a packed bed with zeolite 13x adsorbent operating at a flow rate of 20 standard cubic feet per hour and an inlet concentration of 650 parts per million of carbon dioxide. We optimized the bed length, bed diameter, and the particle critical diameter to reach an optimum operating point with minimum pressure drop across the bed and maximum carbon dioxide captured. The optimum operating point is shown in the table here. The pressure drop across the bed comes out to be less than 0.01 bar, which is well within the compressor limit. Also, the outlet concentration of carbon dioxide is less than 5% of inlet concentration, which indicates no breakthrough. As an additional validation step, we performed mass balance of carbon dioxide across the entire bed over the simulation time. The mass balance is given by a simple relation. The amount of carbon dioxide coming in equals to the amount of carbon dioxide at the outlet plus the amount of carbon dioxide absorbed on the bed plus the amount of carbon dioxide in gas phase in the voids in the bed. As we can see in the slide, the error in the balance is less than 1%, thus validating our model. The same framework can now be used to run simulations for new adsorbents. Simulations for different adsorbents will allow us to make an informed decision in choosing the right adsorbent for the cube. For these simulations, we require Toth equilibrium parameters and the mass transfer coefficients.
In our simulation, the equilibrium loading Q star is determined using the Toth isotherm, which depends on three parameters: Qmax, B, and T. Qmax represents the maximum adsorption capacity. B reflects the affinity between CO2 and the adsorbent, and T accounts for surface heterogeneity. These parameters are obtained by performing equilibrium adsorption experiment over a range of CO2 concentration at a fixed temperature and fitting the data using non-linear regression. For kinetics, we use the linear driving force model. Transient uptake experiments are performed, and from the uptake curve, we determine the half time, which represent how fast adsorption reaches equilibrium. The LDF rate constant is then calculated using KLDF is equals to 0.693 by TF. We also perform this experiment for different particle sizes, since the rate constant depends on diffusion length and scale approximately as diffusion by radius of particle curve. For low concentration conditions like 400 ppm CO2, we analyze how kinetics vary with loading and use the low loading limit to represent realistic operating conditions. Together, these equilibrium and kinetic parameters drive the LDF-based adsorption simulations.
Traditionally, materials like zeolites have been used for adsorption because of their well-defined micropore structure and high thermal stability. However, when we move towards applications like gas capture, especially carbon removal or adsorption involving larger or polar molecules, SBA15 functionalized with TEPA show clear advantages. First, pore structure. Zeolites are predominantly microporous, meaning their pore sizes are typically less than 2 nanometers. This restricts diffusion, especially for larger molecules. In contrast, SBA15 has a mesoporous structure with pore sizes in the range of 5 to 10 nanometers. This allows much easier diffusion and accessibility. Second, surface functionalization. SBA15 can be easily functionalized with amine groups like TEPA, whereas TEPA stands for tetraethylene pentaamine. These amine groups actively interact with acidic gases like CO2 through chemabsorption. Zeolites, on the other hand, rely mostly on physical adsorption, which is weaker and less selective. Third, moisture tolerance. Zeolites tend to lose efficiency in the presence of water because water competes strongly for adsorption sites, whereas the presence of moisture in the case of SBA15 impregnated with TEPA enhances the interaction between the CO2 and the adsorbent, results in the more carbon capture compared to zeolite 13. Fourth, adsorption capacity and selectivity. Due to the presence of multiple amine groups in TEPA, SBA15 TEPA shows significantly higher adsorption capacity and selectivity compared to zeolites, especially for carbon capture applications.
We synthesized SB15 by dissolving pluronic P123 in 2 molar hydrochloric acid at 40 degrees Celsius to form template solution. Tetraethyl orthosilicate, also known as TEOS, was added as a silica precursor at 40 degrees Celsius and stirred for 24 hours to form silica networks. After that, the gel was transferred to Teflon autoclave and aged for 24 hours at 100 degrees Celsius to develop the mesoporous structure. Then the material was calcinated at 550 degrees Celsius to open the pores and remove the P123 template. The calcination ramp was slow, 1.5 degrees Celsius per minute to avoid cracking. Finally,
Tetraethylene pentamine, known as TEPA, was dissolved in ethanol and then impregnated on SB15 by stirring it for 18 hours, followed by drying in vacuum oven at 70 degrees Celsius to get our final adsorbent. Lab coat, nitrile safety gloves, and goggles were worn throughout all steps of synthesis. HCl was handled strictly inside the fume hood to avoid the inhalation of acidic vapors. TEOS is flammable and moisture sensitive, so it was handled away from open flames and in dry environment. Also, TEPA is a corrosive amine liquid, that's why skin and eye contact was avoided and it was handled only in a fume hood. The high temperature calcination was carried out in a programmable muffled furnace, and the heat resistance glove were used while handling hot equipment.
In engineering, safety is the foundation of everything. We built the ChemE cube for fully autonomous and unattended operation. To make that possible, we engineered 3 safety systems directly into our core design. Negative pressure airflow. We used what's called the induced draft design. It means that the vacuum pump is placed at the end of our system. That causes the entire unit to run at pressure lower than the air around us. If a tube ever disconnect or a seal break during operation, the air pulled inward, not outward. It means hazardous gases or duct physically cannot escape our system. Second one is secure column sealing. Primary column is made from lightweight aluminum and uses viewer lock connector, the same connector that found on medical syringe. One simple twist and the column detaches. And the moment it does, it already sealed. Side stay fully contained, no dust escape, no operator ever comes into contact with the chemical inside it. Third one is automatic system recovery. If the dust get past the filter and jam the pump, the motor start pulling more current than it should. Regular fuse would just blow and the entire run get lost. It uses a digital current sensor that detects the spike the moment it happens for the blockage to get clear and restart the pump on its own. These 3 systems ensures that our prototype remains safe and stable throughout the entire run. We are planning to run experiment on various CO2 adsorbent in the lab setup we have to test how much CO2 it captures. Then take this data and use it to fine-tune the value for flow rate and pressure drop so that every single run captures the maximum amount of CO2.
The estimated capital cost of our cube is $665.
Now let's talk about where our product is in the market. The global air purifier market stands at $14.5 billion and the current DAC market is of just $100 million. That's a scale ratio of 145 times. This gap isn't a weakness, it's our entry point. Our approach is quite simple. We don't try to create a new market from scratch. Instead, we integrate our DAC technology with household and commercial air purifiers, collaborating with companies which are already existing in the market. By doing so, we avoid the 3 major hurdles faced by startups, that is scale, distribution, and trust. All these 3 have already been conquered by our partners. For our target market, we are looking at USA and Europe, which together represent $7.2 billion in commercial and household air purifier sales. Household accounts for the largest share, with commercial following closely behind. Now let's look at the estimated market share of DAC integrated air purifiers. Now, to estimate the realistic market share of our segment, we have considered a 4-factor formula, which takes the reference company's market share as maximum and adjusting the category conversion, price premium, and our entry point as startup collaboration. Now let's consider the household market. It has a total addressable market of $4.5 billion. The reference company share is taken as 10%, the category conversion rate is taken as 20%, the premium price rate is taken as 40%, and we have included a safety factor of 40% as well. In other words, we are not entering a new niche. We are riding on top of a pre-existing, mature and trusted $15 billion marketplace and using this as a platform to bring direct air capture into people's everyday lives.
Now, I'll walk you through our business model and how our solution works in a real-time setting. Ambient air is drawn into the unit and it's passed through multiple cartridges. These cartridges contain specialized adsorbent material which captures the carbon dioxide from the air. This system also filters out the pollutants and the purified air is then released back into the environment. Over time, the adsorbent in the cartridges becomes saturated and its performance starts to drop. To handle this smoothly, the system can give a notification through our app that the cartridge has reached a saturation level up to a 90%, or it can notify us through an LED light on the system that it shows that the cartridge is about to reach its limit. Cartridge life is estimated based on the usage patterns, and this allows the user to request service in advance from our app. At that point, our service team visits the site, replaces the used cartridge, and then installs a new regenerated one. The used cartridges are taken back to a facility where the CO2 is safely extracted and the adsorbent material is restored for reuse. Because we reuse cartridges rather than replacing them permanently, this also reduces long-term waste. To put our value proposition simply, in a typical system, an organization would need to invest separately for an air purifier and a carbon capture system, meaning double installation costs, double operation costs, and higher overall costs. Our solution combines both into a single system, reducing duplication and reducing the overall cost of ownership.
First, we generate primary revenue through B2B hardware integration. We sell our DAC module to air purifying companies so that they can integrate it with their air purifying unit. We position it as a premium ESG driven add-on without significantly increasing the consumer cost. Second, we build a recurring revenue system through a cartridge-based system. We will supply the cartridges with the DAC system and we would cater to the customers for their servicing and subscriptions that they have taken. Importantly, the cartridge would act as an enhancement add-on, so if the customer wants to use it, it would help them purify the CO2, and if they don't want to use it, the purifier acts as a normal air purifier. Thus, there is no loss to the core utility of the purifier. From this system, we earn servicing-based revenue, which creates a constant source of income. This can further evolve into a collaborative revenue-sharing system with the partnered air purifying companies. This transforms our model from a one-time sales to a continuous service-driven income. Third, we unlock additional value by processing out the captured CO2. We would be extracting CO2 from the used-up cartridges, and this can be monetized through industrial or sustainable applications. Overall, this creates a system of upfront revenue and recurring income, which would further provide profitability and scalability in the long term.
Many corporations in the US and European Union must meet strict environmental goals to maintain their market value. By funding our rollout, these companies meet their official ESG credits that reduce their carbon footprint while providing us with capital needed to scale globally. Instead of competing with major manufacturers, we collaborate with them. By licensing our DSC technology to companies, we can provide our technology inside millions of purifiers across the world. Each purifier measures exactly how much CO2 it captures. We convert this data into verified carbon removal credits, which we sell to companies in the carbon market, and it acts as an additional source of income. In the US and European Union, government provide tax credits and subsidies to every ton of CO2 removed, making our purifiers affordable while keeping our business profitable. These incentives directly strengthen the revenue model we described earlier. Our DSC technology is a simple, standardized cartridge that fits into existing high-end air purifiers. We don't need to manufacture new machines, we upgrade the ones already in homes and offices.
On this slide, we have mapped the key risks of our DAC integrated air purifier using an impact versus likelihood matrix. Starting with the top right, high impact, high likelihood. These are our critical risks, already visible in today's DAC market. Carbon credit prices depend on policy and market demand, making them highly volatile. Advanced materials and technology lead to high manufacturing costs. With limited global suppliers for specialized sorbents, any disruption in supply chain can halt production and cartridge supply. Low consumer awareness. CO2 removal is invisible, so consumers may hesitate to pay for a benefit they cannot immediately see. Moving to the top left, low impact, higher likelihood, we have strategic risks, including product safety certifications and entry of large competitors. While less frequent, they can significantly impact market access and long-term margins. In the bottom right, high likelihood, low impact, we see operational risks like logistics and manufacturing dependency. Overall, we focus immediate attention on critical risks while planning mitigation for others.